It's surprising what you find in the depths of a department of mechanical engineering, and one of the things that you might not expect to find is biomedical imaging. But I'm here to talk to Anjana, who combines biomedical imaging and bubbles. Anjana, tell me a little bit about your research.
I'm a PhD student with the Mechanical Engineering department, and my research focuses on preparing microbubbles for diagnostic applications. And as the name suggests, these are tiny little bubbles in the micrometer range.
So we're going to start with the sort of the bubbles that people are familiar with, soap bubbles here. So let's blow some soap bubbles.
So this is what I used to love to do when I was a kid.
Yeah. Which are just endlessly brilliant toys.
I know, absolutely.
So let's have a talk about what you're doing as you're blowing the bubbles.
So here we see once we put the wand inside the soapy solution, we end up with a thin film of the liquid forming at the ring of the wand. We start off by blowing a continuous medium of gas, and we notice that just blowing a continuous stream of gas still results in individual bubbles being ejected from the wand. This is because all liquids have a certain surface tension. So when we blow a gas through here, this spherical shape is retained by the surface tension of the liquid.
So these sorts of bubbles are what people are familiar with, and we often see bubbles in the bath and in drinks and all that kind of, those sorts of places. These are big bubbles on the scale of all the bubbles that you can make. And in your research, you make really tiny bubbles. Exactly. So tell me just a little bit first about why you'd want a tiny bubble.
Bubbles tend to reflect ultrasound signals a lot more effectively back to the transducer than our tissues itself. And this is a concept that we'd like to capitalize on. So my research involves essentially trying to make these very small bubbles in an economic way and in a scalable way as well, such that in the end we can ultimately improve the quality of ultrasound imaging and improve forms of diagnosis and treatment to patients. So in order to get bubbles to that diameter, we do have a novel device that we use, which is known as a microfluidic T-junction. As the name suggests, it's in the shape of a T. One of the inlets is where the liquid enters the system, and through the second inlet we have a gas entering the system. Similar to what we did with the bubbles here, we have a single stream of gas, and which essentially blows a bubble in this way. What we have here again is a single stream of gas causing little pockets of air encapsulated with this thin film of the liquid. We use a biocompatible liquid which is easily accepted by the body.
And so it has to be small enough. And how small does something have to be to hitch a lift into our veins and our arteries?
This is an optical microscope image of the tiny little bubbles that we capture. So these are slightly larger bubbles in the 100 micrometer range. However, playing around with the parameters, we can achieve slightly smaller bubbles.
The end goal of this is that one day, you or I might have a medical condition, we might walk into a hospital and the doctors want to see what's going on. And this is the sort of thing that will help them.
This would certainly help them, because if we look at it on a more economic perspective, ultrasound is one of the most economical imaging mediums that we have at the moment. So if we're able to effectively improve the quality of ultrasound images, we can potentially be able to image other parts of the body.
And so it's worth blowing tiny bubbles because it's going to help you make cheap internal imaging quicker and better.